Alrighty, we're moving on to day 3 for 6-1, the section that never ends. Some people think that way. We got a lot of important stuff, though, to talk about in 6-1. Today we're going to look at arc length and area of a sector. So those are the two things that we're going to address. Arc length we've already begun talking about because that was our definition, or how we were thinking about radian measure, that a radian is the length of an arc that's equal to the radius of the circle. Now, we were talking about that in terms of the unit circle, which has a radius of 1. So thinking about what that means, now we're going to take that even further and look at what if the circle doesn't have a radius of 1? What does that mean and how does that work? Because we want to be able to work with no matter what the radius of the circle is. So we're going to do a very similar sort of proof that we did for why does the unit circle SOHCAHTOA ratios work for sine, cosine, and tangent, even if it's not the unit circle. What if the radius is something else? We talked about those proportional triangles. We're going to do a very similar thing here with concentric circles looking at arc length. So in the unit circle, and that's my inside circle in the picture here with the theta and the radius of 1, that's my unit circle. So this intercepted arc would be equal to that angle measurement in a radius of 1. That's my 1. My angle is equal to, when the radius is 1, central angle equals the arc. Now, what if it's not a radius of 1? So if I don't have that one-to-one relationship there, how can I describe the length of the arc? So I'm going to make it more general for this other circle. It could be bigger or smaller than the unit circle as well, but let's just call this radius, so all the way out to this circle, r, for any radius of any circle. And then the arc that they're talking about that we're trying to figure out is the intercepted arc, meaning where the ends of this angle cross or intersect the circle. And the universally accepted letter for arc length is s. I know that seems kind of weird, but s for a distance, that's sometimes used in physics and things like that too. So s is the distance between where those two parts of the angle intersect the circle. So we can set up a proportion because these are concentric circles. The length of the big circle's arc to the unit circle, and then the radius of the big circle to the radius of the unit circle. So the big arc is to the smaller one, so my theta, my arc length in here, as the radius of the larger circle is to the radius of the unit circle, which we know to be 1. So we're going to just solve this proportion. We're going to cross multiply because cross products are equal. So s times 1 would be s, r times theta, and we have a wonderful, quick, and easy little formula for the arc length of a sector, or a piece of the circle. One thing to keep in mind, though, that's really important. Your theta always has to be in radian measure because this is a length of an arc. We are not dealing with a degree measure, we're dealing with a radian measure. So I want to give you a really important understanding of why this is. So if people put in something into this formula, say 30 for a 30-degree angle, if they put that in for theta, 30 degrees and 30 radians are not the same thing. Think about what a 30-degree angle would look like in your head. So visualize 30 degrees. Okay, and then what would 30 radians be? Well, once around the circle is 2 pi. That's about 6.28 radians. So 30 radians would be about 5 times around the circle then. That's a much bigger angle than what 30 degrees would represent. So it's really, really critical that you understand that the theta in these formulas today have to do with the length of arcs. We're talking about radians, so be very careful what you use. All right, so let's just talk about just a straightforward, how is a formula like this going to help you find something. So we're going to look at applications like how far a pendulum swings, or maybe if a road curves, how could we figure out the length of the distance traveled on that road if we know the angle and we know that radius of the circle. So lots of different applications out there. So I'm going to have you go ahead and draw this circle that they're talking about. Draw a circle with a radius of 19, so 19 centimeters. And they say that there's an intercepted arc where the central angle is 171 degrees. Okay, so a central angle, remember what that means from geometry. Think about that for a second. So where's the vertex of the angle located if it's a central angle? Well, that'd be at the center of the circle. And then the angle that they're talking about is 171. Oh, that's a terrible estimate of that. Let's make that a little bit bigger. 171 would be more like there. So 171 degrees. All right, so they want the intercepted arc. That means they are looking at the distance from where the end of this angle meets the end of that part of the angle. So the intercepted arc just means where it crosses. So that's the S that they're looking for. They want the length of that arc. Alrighty. Now, so what we're going to do is we're going to figure out that S using what we know about the circle. So there's two things you need to be able to use the arc length formula. So in a situation like this, always write down the formula that relates what you want. Do we have a radius? Yup. Do we have an angle? Yes, indeed. However, our angle is in degrees. So it's 171 degrees. I cannot just plug in 171 in for theta, because that would be, think about that, in if you just plugged it in now and you meant 171 radians, my goodness, that would be around the circle whatever 171 divided by 6 is. So lots and lots of times, like over 20 times around the circle. So we need to convert that to radians. So how do you convert degrees to radians? What's our multiplication factor? We'd multiply by pi over 180. So you can do that ahead of time and get what your angle measurement would be, so you have that value. Otherwise, you can just do it right in the formula as you find the arc length, which is what a lot of people do since it's multiplication anyway. So 19, our radius, times the 171 pi over 180. And we just go ahead and multiply. So it's really critical we understand that, yep, got to change that into radians. And when you multiply that, you get 56.7. Now, when we have units associated with this, how long is the arc? So look back at what your radius was in. So that would be in centimeters. So that looks like we would be in centimeters here as well. Now I want you to think about if that's a reasonable answer for something with a radius of 19. Now think about what the diameter of that circle would be. If I went all the way across, if it was 19 for a radius, the diameter would be 38. So if I'm going around the circle, it's going to be further than the diameter, but not ridiculously so. The biggest goof that people make is they would do 171 as the angle and times it by 19, forgetting that this is not in radians. And you get a number like that's over 1,000. So I don't remember what it was exactly. But does it make sense that the arc length of that circle would be over 1,000 if your radius was only 19, right? So thinking about that number sense idea, if that's even a reasonable number. So hopefully that'll help you remember what units you need to be in. Okay, the other thing I want to talk about today is something called area of a sector. So a sector is like a piece of the pie. So instead of having the entire circle, we're just looking at a piece of it. And you could figure this out each time kind of individually. If you figured out the area of the whole circle and then what part is that angle, and you could kind of work backwards, but we really can do it by knowing that proportional idea again between sectors and circles. So we can actually come up with a formula for it too. So we don't have to kind of do that every time. So I'm going to set up a proportion using things I think I might know. So I'm going to compare the area of the sector to the area of the entire circle. And then that's proportional to then the arc length of the sector, so the length of the arc, to the entire circle all the way around. And what's that called? The distance all the way around a circle? Circumference. All right, so when we do that comparison, those are proportional. We're taking the sector to the whole circle, length of the arc to the whole circle. We know relationships for a lot of these. Area of the sector I don't know, so I'm going to go ahead and call that A for area. Area of the circle, what's your formula for area of a circle? Pi r squared. Arc length, we just did that, r times theta. And let's talk circumference for a second. There's two formulas out there kind of commonly accepted for circumference. So one of them is pi times the diameter. The other one is 2 times pi times the radius. Taking a look at the other information we have, what do you think would be a better option? That's what I'm going to do, because I already have r's in here, right? So I don't want to have to introduce a new variable. Okay, so how do I solve proportions? Well, cross multiply, because the cross products are equal, and I'm going to be able to solve for, hopefully, my a. So cross multiply, so a times 2 pi r, and then other cross product would be a pi. R squared times r would be an r cubed, and then we'd have a theta. All right, so let's solve for a. I'm going to divide by 2 pi r, divide by 2 pi r. So we get our area is equal to, okay, take a look and see what happens over here. What happens to the pi's? They divide out and leave a factor of 1, so that's nice. Look at your r's. We have an r squared, or r cubed over r. So subtract the exponents, or 3 over 1. One of them would divide out, and we would have just 2 left. So we're going to have an r squared. And looks like we still have a theta. And then we have a 2 on the bottom. So some people put r squared theta just divided by 2. But thinking about that coefficient out front, a lot of people write it like this, just 1/2. Kind of like area formula for a triangle, right? You can say 1/2 base times height, or some people do base times height divided by 2. Same idea. All right, now again, super important that theta has to be in radians. The angle measure that you use has to be in radians because we used arc length to derive this formula. So we really need to be careful that we're thinking about the same things. It's always going to be an angle measurement in radians. So if it's not in radians, you need to put it into radians first. Or if you're solving the equation and you're solving for theta, it's going to come out in radians. So we need to make sure we're aware of our units. Okay, so let's do like a regular situation first, then we'll start putting these together and doing some applications. So it says, find the area of a sector if the central angle measures 3 pi over 7 radians and the radius of the circle is 9.5. All right, so the radius of the circle is 9.5. The central angle, that means theta. So when they say central, it just means the vertex of the angle is at the center of the circle, which is what we need it to be. They say that that's 3 pi over 7 radians. Okay, well, they said the word radians, so that helped us kind of know what we're in. But what if that word wasn't even there? Would you still know that that 3 pi over 7 was in radians? Well, pi kind of gives it away because a lot of the radian measure things have pi in it, but it's not because of the pi. How do you know for sure that it's in radians? What don't you have? And if you're shouting out to your computer, degree symbol, you're exactly right. There's no degree symbol there, so it's got to be in radians. So just make sure that you know that it is. And they want you to find the area. So I would write out the area formula and just make sure that I have everything that I need. So always list what you know, and then write the equations that use the variables that you have and what you want. So it looks like we have the radius, we have the angle. I think we're good to go. So I'm going to do that substitution. And we're just going to multiply on our calculator. So 9.5 squared times 1/2 times 3 pi over 7. What would your units be when you do this? So it's area, space inside, so that would have to be meters squared. And I came up with 60.8. So hopefully you're in the same ballpark for that, for your solving. So not that big of a circle. So 9.5 is the radius only, and 3 pi over 7, that's 3 pi over 6 would be pi over 2. That would be 90. So we're a little bit less than 90. This is a degree 1 angle. So it's not very big. So we shouldn't be expecting a very large angle or a very large area. Let's try another one. I want you to list what you know. So take a moment, pause the video if you need to. Write out all the variables and what values they have and what formula maybe connects them. And then we're going to talk about how do we deal with this then. So pause the video for a second, write out what you have, what you think you know, and then what formula do you think relates them. Okay, so what I was looking at is arc length is S. So that's 8 inches. They say the diameter, careful on this, the diameter is 12. So that means the radius would be 6 inches. So what formula have we been using that uses the S and the R? Well, that's the arc length formula. S equals R times theta. Look at what they're asking you to solve for. They say find the degree measure of the angle. So you are looking for the theta. All right, so let's put in what we know. So that would be 8. That would be 6. Divide by 6. So we get theta equals, now I'm just going to write this a couple different options here, see if all these make sense to you. So you could really write it all three of those ways, right? 8/6 is 4/3, 1/3, 1.3 repeating. Awesome. What units is that angle in? When we use this formula, the theta is always measured in what? Radians. Most people look at that and figure, well, it can't possibly be degrees because it looks weird, but you could have an angle that small. It's in radians because this is the arc length formula we measure in radians. Now, I want to just give you a ballpark idea here. So let's just take a look at the picture. I want you to just be thinking about where would 1.3 radians be? Well, so we have 0. What is halfway around in radians? Halfway around the circle, 180 degrees is equal to how many radians? Well, that's pi, or 3.14. Okay, so just to give you a benchmark, halfway around 3.14. All the way around is 2 pi. That'd be about 6.28. Okay, what I want you to be able to figure out is what's going on up here. What would that number be? If halfway around is 3.14, how would you figure out here? Try a calculation on your calculator, see what you come up with. How would I find here if I know this is 3.14? Hopefully you're coming up with 1.57. That's taking the 3.14, just divide it by 2. It's halfway there. So if you know that this is 3.14, this is about 1.57 radians, where would 1.3 repeating be then? Well, it'd have to be in quadrant 1, somewhere between 0 and 1.57, probably closer to 1.57 than it is to 0, right? Because 1.3 is more than halfway. So getting just kind of this gut feel, like where is this angle going to be? Just to fill out the rest of it, how could I figure out down here? If I know this is 3.14, I've got to go another halfway. Well, another halfway is the 1.57. So if I do 3.14 plus 1.57, I can get my in between. So halfway between a 3 and a 6 is going to be about a 4.7. So benchmarks, where are we in radians? All the way around is about 6, halfway is around about 3. Quarter of the way then is going to be 1.5, 3/4 is about 4.7, just to get a benchmark. Okay, so let's finish off this one then. They want the degree measure of your angle. Degree measure. You have radians, so now you need to convert that radian measure and make sure you use an exact ratio. Don't type in like a 1.3 on your calculator. How do you convert degrees into, or pardon me, radians into degrees? What's your conversion factor? Halfway around the circle in radians was pi, halfway around the circle in degrees is 180. So we're going to multiply by 180 over pi. So just be careful. Make sure you do that conversion if that is what they're actually looking for. If they just say find the angle, you would have been totally fine to just leave it in radians. So I came up with 76.4 degrees. Now, reasonable? We knew it was a quadrant 1 angle, right? A little bit closer to 90 than it was to 0, so 76 fits in right with what we were thinking. So just make sure you understand what that formula is giving you. Okay, I want you to do the exact same thing on this one. I want you to pause the video after you listen to the directions here and figure out, what do you know? List every variable that they gave you a number for. What is that equivalent to? And write every formula that you think might use those same variables. And then let's see what we have. So go ahead and pause the video and jot down what you know. All right, so as I read this, they say the area of the sector is 50 square centimeters. So I know that A for area. And I know that the arc length is 4 centimeters. All right, so they want you to find the radius and the central angle. So radius means find the r, central angle means find the theta. All right, so let's write every formula that we know for this. So the area formula is 1/2 r squared theta. Arc length formula is s equals r theta. I'm going to put in the values that they gave me. So the s is 4, and the area is 50. Okay, now I want you to think for a second and pause the video if you need to. You've got 2 equations, so 2 different equations that we're working with, and 2 unknowns. I want you to think about what strategies could we use to solve for that. So you may have to pause the video, think about that for a second. All right, 2 equations, 2 unknowns. Hopefully most of you are coming up with some sort of replacement or substitution here. When we have a system of equations, so we have more than one and more than one variable, normally that means then we're going to try to be doing some sort of replacement or substitution. You just can't solve an equation with 2 variables one at a time. So let's look at the easier equation, or the one with less maybe in the expression. So this second one here, is there a variable we could solve for? Well, we could solve for r or theta. Doesn't really matter. Looking ahead, when you have to substitute it into the other equation, if I put it in for theta, might be a little bit easier than substituting in for r, just because I wouldn't have to square something then. Honestly, doesn't make any difference at all. You can solve for either one of them. All right, so I'm going to solve this 4 equals r times theta. I guess I'm going to solve it for theta. I'll make that substitution. So theta is equal to 4 over r, and I'm going to take that expression and I'm going to replace it into the other equation for theta. All right, so 50 equals 1/2 times r squared over 1 times 4 over r. Now I want you to think for a second why I said r squared over 1. Both of the other 2 things, expressions on that side of the equation, are fractions. It is super helpful if you put the other one as a fraction then, so you don't have just this big r squared floating in the middle, and then people don't know, is it in the numerator or is it in the denominator? Take care of yourself a little bit with your algebra here. Make sure they're all fractions. So let's simplify that. So we'd have 4r squared over 2r. We just need to reduce that. So it looks like that would be 2r. equals 50, so r equals 25. And let's get some units on that. That's r for radius. Everything was in centimeters, so it'd be 25 centimeters. So the radius is 25 centimeters. Now, in substitution, once you have one of the variables, I can take that now and plug it back in. So I get 4 over 25. It's theta, so it's a central angle, and tell me what units we're talking. In the formula, when we solve for it, that comes out in radians. So this is a radian measure, so that's radians. Now go back, did it specify how they wanted your angle? It just said find the central angle. So have you found the central angle? Sure you did. It's in radians. You can write it as a decimal too if you want. I think it's 0.16 about. So if you think about like where is 0.16 in your radian measure, I'm going to go back to my picture here from before. So first quadrant is 0 to 1.57. 0.16 is going to be pretty tiny in that first quadrant because it's not even a 0.5. It's not even halfway there. So it's pretty tiny, but it's a radian measure, which is fine. If you wanted to, just so you could see what it is, you could convert it to degrees if that's an easier way for you to look at it. Multiply by 180 over pi. I think you get like 9.2 degrees or something. It's pretty small, but it didn't specify, so you could really leave it as pi or 4 over 25 radians, and you're perfectly fine. So just being confident and comfortable in working with those two formulas, so arc length and area of a sector, and being able to understand some of the applications that go with them. And that's really what you're going to get into when you start talking about the some of the applications in the homework assignment today too. So this day 3 for notes, day 2 for the book assignment is back on page 348 again. So give those a try, and then we'll see how we're doing on arc length and area of a sector.